day 4 of Taylor series. Big thing today is we're going to start figuring out how to find the sum using Taylor series and other series, and then putting it all together in a free response from stuff we've already done before with Taylor series. So first off, we're going to be finding the sum of these first 3 problems. And there's only a couple ways to find the sum. So the first off way is we can find the sum if it's a geometric series. Okay, so if it's a geometric series, if there's a formula for that, we can actually find that infinite sum. Or if we can rewrite as a Taylor series. So those are the 2 big ways to go ahead and find these sums, or at least the 2 ways that we're going to really talk about. So if you look at this first one right here, what you want to do is you want to find the exact sum. So this is infinite. So you really can't do that unless it's a geometric, which it's not by looking at it. So I can't do that. So I have to rewrite this as a Taylor series in order to find this sum. So what Taylor series does this kind of sort of look like? Well, it looks like e to the x. Because e to the x is 1 plus x over 1 factorial plus x squared over 2 factorial plus, and you get the idea. So this kind of sort of looks like this, does that not? So we got 1, and then 3 over 1 factorial. See how these are all factorials? The only difference is that we're plugging in a 3. So when x equals 3. So the sum of this series is e to the x when x equals 3. So the sum is e to the 3rd. Okay? So this was an instance where we found it to be a Taylor series that we're familiar with, and then we just plug in the x value. Same deal is going to happen here for this one. So if you're looking here, I'm seeing odd factorials, so that's going to kind of scream to me, it's probably sine. It's probably sine. So this one looks just like a sine here. So sine of x, which is going to be 1 over. I'm just looking at this right here. Yeah, it's right here. So this is going to be sine of x. So actually, if I'm looking at this, this is going to be sine of 2. Okay? Because what is our sine of x here? Wait, this is not sine of 2. This is actually sine of 1/2. What was I thinking? This is sine of 1/2. Reason is because what is it? X minus x the 3rd over 3 factorial plus x the 5th over 5 factorial. Sorry, give me a second there to kind of figure this one out. So if I'm looking at this, it almost matches exactly because of the denominators. The only difference is the x value is 1/2. So this one is sine of 1/2. Okay. And now let's look at this final one right here. This actually is a geometric series. I can just tell from right here where my r is negative 2/3. In my a sub 1 value, there's no coefficient in front of it, is 1. So my sum for a geometric here is going to be a sub 1 over 1 minus r. So I'm going to get 1 over 1 minus negative 2/3. That's going to end up giving me 1 over 5/3, which is just 3/5. All right, so those are different ways to find the sum. There's actually a couple more ways to find it down here with this theorem here. So what's really just trying to say here is if you're given this Taylor polynomial, right, Taylor series, it has a radius convergence of r greater than 0, and it's got to be differentiable, and therefore it's continuous, and it's the derivative antiderivative are as follows. So f prime of x is equal to the sum. Okay? And the antiderivative of x is equal to this sum right here. Okay, so these are connected. These are different ways to find exact values, and this is just using derivatives. So we'll be using this in the problem coming up. So what's going to end up happening here is we're going to have a we are going to have just some type of free response here, and we'll get to that theorem here. I think it's in part C that we use it. So first off, says write the Maclaurin series for f. Give the first 4 non-zero terms in the general term. So if you're looking at this right here, this is a geometric sum. So a sub 1 is equal to 1, r is equal to x. So this is actually going to be 1 plus x squared plus x to the third, which we have done that in a previous video. So our general term is x to the n. Okay. And when does this converge? And again, this is all from the one of our previous videos here. It's going to converge from -1 to 1. Okay, because r has to be less, the absolute value of r has to be less than 1. We did that in the previous video. Okay, so now use your answer in A here to find f prime. So give the first 4 non-zero terms in the general terms. Let's go ahead and do that. So f prime is going to equal, so I need to find the derivative of 1, which is 0. So that's nothing. Derivative of x is 1, plus derivative of x squared is 2x, plus derivative of x to the third is 3x squared. Now I need 4 terms, so even though the 4th term isn't here, I do know that the 4th term is this x to the 4th plus dot, 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 dot. So I do know that. So I'm going to find the derivative of that, so which is going to be plus 4x cubed plus dot, 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 dot. Plus, what's the derivative of this x to the n? It's just going to be n x to the n minus 1. It's still going to converge, the same radius convergence here. So it's going to converge from -1 to x to 1. That's not going to change because it's a derivative for this example right here. So then it says, for what values does x converge? Okay, yeah, got it. I'm just making sure that I've got everything here. So it's going to converge right here. All right, and here's the other radius of convergence. Just double checking my notes real quick, make sure I'm not missing anything here. Okay, so it looks like I do have to check the endpoints for this one, just because it's not a geometric series. This one right here, the f prime. So I do need to check the endpoints. If x were to equal 1, by the way, then we would get a series of n, and that's going to diverge because it gets bigger and bigger and bigger every single time. So if x is equal to 1, it's going to get bigger and bigger and bigger. X equals -1. Same thing here. It's not decreasing in magnitude either. So the endpoints are not going to converge here. So that's why that is going to work out right there. All right, now C, this is when we use our theorem that we just learned. Use your answer in part A to find the sum of the infinite series. So what we kind of have to do here is what is done to get to this, right? So what have you done to get to this right here? So and it says use our answer in part A. So it's related to this somehow. So what was done to get to this? So if I'm looking at my previous stuff here, it kind of sort of looks like this guy right there. Isn't that 1 plus 2 over something, plus 3 over something, plus 4 over something? Very, very similar. So this looks like f prime. Of what value? Well, if that's over 3 squared, so it looks like it's going to be f prime of 1/3. Okay? So it is f prime of 1/3 is this right here. And this is just by looking. So you have to do a little bit of by inspection type of deal here. So since that is equal to 1/3, I'm going to just find f prime and then plug in a 1/3. So what is f prime? And it's of this guy right here. So real quick, f of x, I'm going to rewrite this as 1 minus x to the -1. Just easier for me to take the derivative of that. So I'm going to do derivative of the inside, which is -1, times derivative of the outside, which is going to be -1, 1 minus x to the -2, which is going to turn into 1 over 1 minus x all squared. So now f prime of that 1/3, plug that 1/3 into there. I'm going to get 1 over 1 minus 1/3 squared. 1 over 2/3 being squared, which is going to be 1 over 4/9, which is really equal to 9/4. So I can find the exact sum again, knowing that since this is the derivative of a series. So, right, now use your answer in A. And to find the Maclaurin series for this guy right here, give the first 4 non-zero terms. So what we're doing here is, so same idea here. With not taking the derivative, now we're going to take the antiderivative. So here it is. So from 0 to x of f of t deep t. I'm just taking the antiderivative of each of these guys up here. That's all that really is saying. So antiderivative of 1 is going to be x. Antiderivative of x is going to be plus x squared over 2 plus x cubed over 3 plus x to the 4th over 4 plus, you get the idea, right? So this is going to be plus x to the n plus 1 all over n plus 1. Okay, so that's what that equals here. Because it's from 0 to x, all I'm doing is replacing all of these t values. Actually, I kind of didn't show that work. I'll show that real quick. So what this really is, kind of went right to the answer here. Probably should explain it a little better than that. So all I'm going to do is just change this into t and take the antiderivative. So this would be t plus t squared over 2 plus t cubed over 3. Get the idea, right? If I get that from 0 to x. So that's why I'm just going to plug in an x into these and then plug in a 0. 0 is going to cancel everything out. So I'm going to go ahead and find the values of which values does it converge. Okay, so again, I'm going to have this. And I do need to check the endpoints. All right, I didn't formally check the endpoints up here. I probably should have. Maybe I'll come back to that one in just a second. I do need to formally check these endpoints. So let's go ahead and do that with blue. So let's do an x is equal to 1. So when x is equal to 1, I'm going to get the series of x to the n plus 1. So it's just going to be 1. So it's 1 over... That's it, just 1 over n plus 1. Why is it not? My notes are saying something a little different. No, it should be this. Okay. So when that happens right there, this is actually going to diverge. Okay, I can use the comparison test. I can compare to n equals 0, 1 over n, and this is going to diverge because it's harmonic, because p is equal to 1, right? So it's going to diverge by p series. So I'm going to compare these two. This is going to diverge by direct comparison test. All right, because since this diverges, this one's larger, so this is going to diverge as well. So with x equals -1, get something very similar here. So I'm actually going to get, so if I'm plugging in a -1, it's actually going to start to alternate here. So I'm going to get -1 to the n plus 1 all over n plus 1. And so this is alternating. This is going to be decreasing in magnitude. Find the limit is going to go to 0. So therefore, this one's going to converge by the alternating series test. So this converges right here. So I'm actually going to have a little guy right there. So it will equal for that one. Okay, like I said, I probably should have formally went up here to do this one as well. I'll real quickly do that. So when x is equal to 1, I'm going to get the series of just n, and this is going to diverge by nth term test because the limit's going to equal a non-zero value. And when x is equal to -1, right up here, I'm going to get -1. I'm going to get alternating because we get -1 to the n minus 1 times n. And this is going to diverge, again, by the nth term test. So it's going to also diverge by the nth term test for both of these. So that's why that one, the raised convergence, endpoints don't check out. This one, endpoints do check out. Remember, again, here, I'll put this in pink so that it looks a little better. All right. Okay, finally, long for response here. Use your answers in D to find the sum of the infinite series. Beautiful. So we did one with finding the derivative from our theorem. So this is going to look, again, very similar to this. This is just going to be the integral from 0 to x. Now, what's my x value right here? It looks exactly the same. So x is the 1/3. All right, so x is going to be 1/3 of this function. Okay? So this is going to be my sum. So this, if I were to do just some baby use up here, I would get negative ln of 1 minus t. Evaluate that from 0 to 1/3. So this is going to give me negative ln of, plug in a 1/3, I'm going to get ln of 2/3 minus a negative ln of 1, which is just 0. So I'm left with negative ln of 2/3, which, by the way, we can put that as a power. So it's ln of 2/3 to the -1, which is the same thing as ln as 3/2. So any one of these answers is good right there. So we use the theorem for part C and for part E to go ahead and make sure that we can find the sum using the theorem right here. So really that's what we did here for parts B through E. We just used this theorem. So that's all we're talking about today for Taylor series, day 4, using that theorem to find sums using derivatives and antiderivatives of Taylor series.